In this lecture, we'll talk about the types of problems that we'll solve. Then we'll talk about the general problem-solving procedure. And finally, we'll talk about applications to multiple unit operations. The types of problems that we'll talk about are ones that involve a single unit operation. This has been the majority of problems we've considered thus far. Then just recently, we started talking about multiple unit operations that consist of two or more single operation steps. And this will conclude then with a discussion of recycle and bypass within processes, which leads to more complicated problems. For these problems, we use our general conservation of mass equation. It's illustrated here as accumulation within a control volume is equal to the input of mass into that control volume minus the output plus generation minus consumption. This equation often is abbreviated as A is equal to I minus O plus G minus C. We're going to apply this conservation of mass equation in two ways. First, we're going to apply it to total mass, the total amount that enters or leaves or in a control volume. When we talk about total mass, the G and C terms, the generation and consumption terms, are zero, always, because we cannot generate mass or consume mass. However, when we talk about applying our conservation of mass equation in individual chemical species, the generation and consumption terms may not be zero if chemical reactions occur. Up to this point, all the problems have not involved chemical reactions, and we won't be considering chemical reactions for another week. To reiterate, our initial problems are going to involve steady-state processes for which accumulation is equal to zero, and we won't be having chemical reaction occur so that generation and consumption terms are zero. So this leads to a reduction of our general conservation principle to one in which we can say 0 is equal to input minus output, or input is equal to output, in is equal to out. Just briefly to review the problem-solving procedure, we follow these 9 steps. Sometimes it's not in a sequential fashion, but at some point we'll have to consider each of these 9. The first is just to read the problem statement carefully. There often is information embedded in the statement that we may not appreciate at first, and there could also be information we don't use at all. Second, we need to draw a process flow chart and label the streams. Third, we need to convert all information to a common set of units. These will either be mass units or mole units, since we're applying our conservation of mass equation. Fourth, we should review our process flow diagram and look at all the streams and see if there are at least one flow rate or amount specified. If there are no flows or amounts specified, then we're free to choose a basis for our calculation. Typically, this is a uniform number like 1, 10, 100, with the units that are appropriate for the problem. So for example, you might say the basis is 100 grams per second, a mass flow rate. Once we solve the problem for a given basis of calculation, we can scale it to any other value by simply multiplying each of the flow rates or amounts by the same factor. The fifth step is to assign variables to unknown flows and compositions for each of the process streams. Next, for a control volume that we are considering, we're going to perform a degree of freedom analysis. And if we can solve, then we're done. If not, we either have to go back and reread the problem statement, go back to step 1, and see if there's any additional information we can use, or we're going to have to consider a different control volume. Next, we'll draw that control volume for our balances, and we'll write those mass balances out in step 8. We'll write overall balance. For each control volume, we'll write an overall balance and a balance for each of the species. And then we'll attempt to solve for one of the unknown variables associated with that control volume. Sometimes we can solve for one at a time, but there are times in which we have to solve multiple equations and multiple unknowns, as we've done previously when we had to solve 2 equations and 2 unknowns. And finally, step 9, there are often additional quantities that are asked to be calculated, and we'll have to do that. When we talk about a single unit operation, only one control volume can be drawn. When we have multiple unit operations, there are multiple control volumes that we consider. We can consider a control volume around each of the unit operations, for any combination of the unit operations, of adjacent unit operations. And we also have to consider, we can consider control volumes around points where fluid streams are mixed or where they're split. And we'll be having an example of a mixing point in the problem we work in this lecture. This is a problem we'll be looking at in this lecture. We're only going to look at one problem in this lecture, because as we start adding unit operations, problems become more difficult and more time consuming. And this particular problem will take up the whole time that we have available. This process flow diagram consists of two units, a unit 1 and a unit 2. There's one feed to unit 1. This feed then is split into two streams, a product stream that's removed from the bottom, and a second product stream that's sent to this point right here, which is a mixing point. This product stream from unit 1 is mixed with this stream at this mixing point. The mixture is then fed to unit 2. Unit 2 produces two product streams, one that comes out the top and one that comes out the bottom. We're going to finish labeling all the streams that you see here on the process flow diagram. If you glance at them, you'll see that they're not fully labeled yet. But first of all, let's talk about the different control volumes we could consider for solving for unknown flows and compositions here. The red control volume you see here, that's labeled control volume 1, is the overall control volume. It contains unit 1, the mixing point, and unit 2. If you look at the streams that cross this overall control volume, we have the feed to unit 1. This bottom product from unit 1 crosses the control volume. This feed to the mixing point crosses two product streams from unit 2 cross it. A second control volume is shown here. This red square is drawn around unit 1. And this particular control volume has three streams that cross it. The feed to unit 1, the bottom product from unit 1, and then the second product stream from unit 1 that gets mixed with this stream here. The third control volume is shown here. This control volume is around the mixing point. This mixing point has one input stream, which is one of the products from unit 1. The stream we're going to mix with that product from unit 1, and then the mixture that's fed to unit 2. A fourth control volume is shown here. This control volume has three streams that cross it. The first is the feed to unit 2. Then we have the two product streams that leave from unit 2. We'll perform a degree of freedom analysis for each of those four control volumes from which one we can solve. Now, four control volumes are shown here, four possible control volumes, but there are other choices. For example, we could consider a control volume that goes around the mixing point and unit 1. Usually we don't consider those. We'll typically look at control volumes around individual units and then an overall control volume around the whole process. Now let's finish labeling all the streams on this process flow diagram. In some cases we have flow rates given but no composition. In some cases we have composition and no flow rate. And in some cases we don't have either. Let's start with the feed to unit 1, this stream here. This stream looks fully specified. If you look at it, a flow rate is given, 800 grams per second, and we have a composition, a mass fraction of A and B given, which sum to 1. However, if we look through the rest of the process flow diagram, we see that there is component C that's introduced here, and therefore C is expected to appear in this product stream from unit 2, the bottom product stream, as well as the top product stream, unless we're told otherwise. So it might be wise to go ahead and label this stream with the composition of C, which we know is 0. In this slide, we've added that information, that the mass fraction of C is 0. Now, let's progress looking at the first product stream that comes out from unit 1. This stream is labeled with a given amount, or flow of A. And if we look at this, we're told that this is pure A. It just reinforces this statement right here, that this is pure A, which leads us to conclude that there is no B and C, and we'll label it accordingly. So for the stream that comes out, the bottom product from unit 1, we've labeled it with a flow rate of 100 grams per second. Mass fraction of A is 1, and the mass fractions of B and C are both identically 0. Let's move on to this stream that's introduced at the mixing point and is mixed with the second product stream from Unit 1. This stream, we're told, has a flow rate of 200 grams per second of C, that it's pure C. And so like the bottom product from Unit 1, we're going to label it as having a mass fraction of C of 1 and the other two mass fractions being equal to 0. The results of that labeling are shown here. The flow rate is specified as 200 grams per second, and the mass fraction of A and B are both 0 because this is pure C, and the mass fraction of C is equal to 1. Next, we're going to talk about labeling this second product stream from Unit 1 that's fed to this mixing point. Then we're going to be labeling the mixture that's produced by mixing there. If we look at both of these streams, the stream here that goes into the mixing point and this one that comes out, there's no information given. So we'll have to use variables for each of the flow rates in each composition. The stream that leaves, the second product stream that leaves Unit 1, we're going to label the flow rate as m dot sub 1. And then we'll label the composition of the stream as x1 representing the value of the mass fraction of A. We know the stream has no C in it, so it's going to be 0. C only appears after the mixing point. Therefore, if these mass fractions all sum to 1, the mass fraction of B will have to be 1 minus x1. So this stream now is fully labeled. We know nothing about it, but we have variables for all the things we don't know. Let's move on to the stream that's produced after the mixing point. This stream now is fully labeled. It has a flow rate, which we're going to represent by the variable m2. It's unknown. The mass fraction of A, we're going to do. The mass fraction of B, we're going to denote as y2. And the mass fraction of C, we're going to denote as 1 minus x2 minus y2, since the mass fractions of A, B, and C have to sum to 1. The stream now is fully labeled. Let's progress on to the top product from Unit 2. We see that there's an amount given, or flow rate given, but there's no composition data. So we'll have to use variables to represent the unknown values. So down below, we've represented the unknown composition of A as y sub 3, and the unknown mass fraction of C as 1 minus x3 minus y3. Once again, the mass fraction of C can be written as you see here, because the sum of the mass fractions of A, B, and C must equal 1. Now let's move to this last stream here, the bottom product from Unit 2. We see the composition data is fully given. Let's just check it. Does that all sum to 1? If you go through here and you add up these, you can either use a calculator or you can just do it in your head. You'll see that they do indeed sum to 1. So the composition data is acceptable, but there's no flow rate given. So we'll have to assign a variable for the flow rate. We'll use the variable m dot sub 3 to represent the unknown flow rate of this bottom product from Unit 2. Now, this process flow diagram is fully labeled, and we can consider the 4 different control volumes that we talked about before and see if the number of unknowns is equal to the number of equations for any of those 4, and thus the problem could be solvable. What's shown here are those 4 control volumes just redrawn. What I'd like for you to do at this time is to count the number of equations for each of the control volumes, that determine the number of equations you can write for each of the control volumes, 1, 2, 3, and 4, and then list the number of unknowns that are associated with each of those control volumes, 1, 2, 3, and 4, and then compare the two to see if the number of equations that you can write is equal to the number of unknowns. Now the number of unknowns is straightforward to calculate. You just consider each of the streams that cross the control volume boundary and then count the number of unknowns in those streams. And as we talked about before, the number of equations is going to be equal to the number of components, the maximum number of components that appear in the streams that enter or leave the control volume. Be careful with this problem because not all the control volumes have the same number of components in them. So take a moment. I would recommend pausing and see if you can fill in this table on your own. As a warning, I'm going to be moving on to the next slide in which The number of equations and unknowns are shown for each of those 4 control volumes. Let's review some of the results shown here. Let's start with control volume 1, which is the overall control volume drawn around both units in the mixing point. If we count the number of equations for this overall control volume, we have to first of all determine the number of components. And if we look at the streams that leave from Unit 2, we see that there are 3 components in these 2 streams. There's an A, B, and C is present in each of those streams. Now A, B, and C are not present in the feed to Unit 1, but there is C present in the feed to the mixing point, which then it ends up in the products from Unit 2. So because there's 3 components, there'll be 3 equations. The number of unknowns, we're looking at each of the streams and counting the number of unknowns in them for those streams that cross across the boundary for this control volume. Note that streams within the control volume we don't have to consider. So for instance, this stream, this product stream that leaves Unit 1 and sent to the mixing point, we don't have to worry about the unknowns associated with it or the unknowns associated with the stream that's produced after the mixing point, since both streams are totally enclosed within control volume 1 and don't cross its boundary. So let's go around control volume 1, starting here at the feed to Unit 1. There are no unknowns in the stream here. If we move around clockwise, the stream here that enters into the mixing point is totally known. There are no unknowns here. If you look at the first product, the top product from Unit 2, there are 2 unknowns associated with it, X3 and X4, or X3 and Y3. I spoke there. And those 2 unknowns are listed here in the table. If we keep on going around, we see there's 1 unknown associated with this stream, and that's its flow rate, M.3. That also is in the table here. If we keep on going around for the bottom product from Unit 1, we see that there are no unknowns associated with that. So the number of unknowns is 3, which is equal to the number of equations we can write. So we can solve for the unknowns associated with that overall control volume. Next, let's look at control volume 2, which is the control volume around Unit 1. To determine the number of equations, let's go around this control volume and look at each of the streams that cross the boundaries of it and determine how many components are in those streams. In this first stream that enters into the control volume around Unit 1, there are 2 components. The feed to Unit 1 has A and B. This product from Unit 1 has 2 components, A and B. And this product, the bottom product from Unit 1, has 1 component, A. If we count up the number of unique components there, we only have 2. A and B are only present in unit operation 1. Therefore, the number of equations is going to be equal to 2. For the overall control volume, remember there are 3 equations because there's a 3rd component that's present within that overall control volume. But there's only 2 components that are present in the control volume around Unit 1. Let's count the number of unknowns for Unit 1. The feed to Unit 1 has no unknowns associated with it. This product from Unit 1 has 2 unknowns, X1 and M.1. M.1 is hiding underneath the 2 there, but I think you can remember that there is an unknown flow rate there. So X1 and M.1 appear in our table over here as unknowns. The other stream that exits from Unit 1, the bottom product here, has no unknowns associated with it. So the total number of unknowns for control volume 2 are 2. That's exactly equal to the number of equations. There are 2 components inside that control volume. The rest of the control volumes, the analysis is shown here. For the mixing point, there are 3 components associated with the streams that flow into and out of that control volume, but there are 5 equations. And for control volume 4, there are 3 equations we can write because there are 3 components, but there are 6 unknowns. So based upon this preliminary analysis here, it appears that we should be able to solve the mass balances for control volume 1 and for control volume 2 for the unknowns associated with those control volumes, the unknowns that you see here. Once we have those unknowns, hopefully we'll be able to solve for the unknowns associated with control volumes 3 and 4. So let's start with the overall control volume 1, which is drawn here. As we just talked about, there are 3 unknowns, a fraction, x sub 3, which is the mass fraction of A in the top product from Unit 2, y sub 3, which is the mass fraction of B in the top product from Unit 2, and then m dot 3, which is the flow rate of the bottom product from unit 2. There are 3 components in the streams that cross the boundaries of this control volume. A, B, and C are present, so there are 3 equations that we can write. There's actually 4. We can write a mass balance for each of the components, but we can also write an overall mass balance. But we know that only 3 of those 4 mass balances are independent. Therefore, since the number of unknowns is equal to the number of equations, independent equations, the problem is solvable. So let's write the overall mass balance for this control volume. And we'll work our way to the control volume, starting on the far left and working clockwise. And we'll determine the total flow rate going into or out of the control volume for the streams that cross the boundary. So let's start over here with the feed to unit 1. The total flow rate is given above the arrow representing the stream. It's 800 grams per second. So we'll put 800 grams, or the value 800, on the left-hand side of the equal, representing an input into control volume 1. We work our way around. We have another input into the control volume, which is 200 grams per second here. That's a total flow rate. So we'll add to the 800 200 as an additional input. We keep on going around clockwise. We have a first output here, which has a flow rate of 475 grams per second. So we'll set this we'll put that value on the right-hand side of the equals as an output, 475. We keep on going around. We have another output, which has a flow rate of m dot. Add this to the right-hand side of this equation. If we keep on going around, we have one more stream. That's an output, a flow rate of 100 grams per second. We'll add that too to the right-hand side. Now we've identified all the inputs and outputs, and we've written them into the overall mass balance here. On the left-hand side of the equals, we summed up the inputs. On the right-hand side, we summed up the outputs. And this turns out to be an equation we can solve for m dot 3. If you rearrange this, simply add 800 and 200 together to get 1,000, and subtract off 475 plus 100, which is 575. We find that the flow rate of the flow rate m dot 3 is 425 grams per second. So we're on our way. We just have 2 more unknowns to solve for. X3, the mass fraction of A, product from unit 2, and Y sub 3, the mass fraction of B, and the top product from unit 2. To solve for the mass fraction of A, it makes sense to consider the conservation of mass equation for component A. And the way we do this is that we're going to go around the control volume, and for each of the streams that cross the boundaries of this control volume, determine the flow rate of component A in those streams. If it's an input, we'll put it on the left-hand side of the equal sign. If it's an output, we'll put it on the right-hand side. We'll sum all the inputs on the left and sum all the outputs on the right. So let's start off here with this input to unit 1. In order to calculate the flow rate of A in this stream coming in here, we look below the arrow to determine the mass fraction of A, which is 0.2. We take that and multiply by the total flow rate, which is above the arrow, a value of 800. That product of the mass fraction of A times the total flow rate gives us the flow rate of A. So if you see down here in our balance, we have 0.2 times 800, which is the flow rate of the stream entering into unit 1. That gives us the flow rate of A entering. Let's work our way around this control volume. The stream here that cuts across the boundary, in order to determine the flow rate of A, we'll take the mass fraction of A, which is 0, times the total flow rate coming in. Well, 0 times 200 is 0, so we don't add anything over here on the left-hand side. A does not enter with this stream. No A enters with this stream. If we keep on going over, we have this stream here to consider. To calculate the flow rate of A in this stream, we go below the arrow to find the mass fraction of A, which is x sub 3. We're going to multiply that by the total amount, which is given above the arrow as 475. So we look in our mass balance for A down here below, we see we have the product of 475 times x sub 3. This is the flow rate of A in the top product. We'll add to it the flow rate of A in the bottom product. This is an output as well. To calculate the flow rate of A in this stream, we go below the arrow to find the mass fraction of A, 0.012. We'll multiply it by the total flow rate, which is given by m dot 3, and it's above the arrow. So if you look down here, we'll have 0.012 times m dot sub 3, but we already determined m dot sub 3 is 425, so we just put that number in here. We don't have to use this symbol anymore. We know that it has a value of 425. Let's finish off this mass balance by continuing around our control volume to find the last stream that exits. This is the stream here, the bottom product from unit 1. Determine the flow rate of A in this stream. We take the mass fraction of A, which is 1, times the total flow rate, which is 100, and we'll put that over here as an output in our mass balance equation. So what we find is that there are 3 outputs. We just have to sum those all up to get the total amount of A that comes out. Set that equal to the amount of A that comes in. Looking at this equation, this turns out to be an equation for x sub 3 that we can solve. I'm not going to go through the algebra here, but if you rearrange this, you can solve for x sub 3. And you can find that x sub 3 is equal to 0.116. Now, if we consider a mass balance for B, we should be able to determine y sub 3. The mass balance for component B is shown here, and we're going to apply the very same thing we've done for component A for component B. We're going to go around our control volume, the overall control volume here, and for each stream that crosses it, determine what is the flow rate of B either into or out of this control volume. So let's start with this stream that comes into unit 1 here. The stream, to determine the flow rate of B in it, we take the mass fraction of B below, which is 0.8, and multiply it by the total flow rate above, which is 800. So we take 0.8 times 800, we put that on the left-hand side of the equals in our mass balance for component B. Let's continue working around the control volume. What's the flow rate of B in this stream? Well, we take the mass fraction of B, which is 0, and we multiply it by the total flow rate, which is 200. This turns out then to be 0. There's no B in that stream, so we don't add anything over here as an additional input in our mass balance, since there's no B in the stream that's fed to the mixing point. Let's keep on going around. So this stream right here, to determine the mass flow rate of B in this stream, we take the mass fraction of B, y sub 3, and multiply it by the total flow rate, which is 475. So we have 475 times y sub 3. That's the flow rate coming out in this stream of component B. If we keep on coming around, we now have to calculate the flow rate of B coming out in this stream. Well, the stream has a mass fraction of B equal to 0.558. We're going to multiply it by the flow rate, total flow rate of the stream, m dot sub 3. Down here in our balance, we have 0.558. Now, instead of using the variable m dot sub 3, we've already determined that that has a numerical value of 425, and we'll substitute it right here. We keep on going around a control volume to find the other stream, the last stream that crosses the boundary. We have an output here, which is the bottom product from unit 1. The stream has no B in it. The mass fraction of B is 0, so it will not add anything to our mass balance that we've written here. Mass balance is complete. If we look at this, we can see this is an equation we can solve for y sub 3 with some simple algebraic manipulations. And if you do that, as shown here, you find that the value for y sub 3 is 0.848. So we're done. We solve for m dot sub 3, we've solved for x3 and y3. The values that we calculated are shown here. And we've updated our process flow diagram so it shows all the known quantities. Balances around unit 1 and unit 2 are going to allow us to calculate the other unknowns. m dot 1 and x1 for this second product stream from unit 1, m dot 2, x2, y2 for the stream the mixture that's produced at this mixing point. Those are the remaining unknowns, and if we apply our conservation of mass equation for our control volume around unit 1 and unit 2, we'll be able to determine those unknowns. I'm not going to show that here. This is the end of the lecture for now. What we're going to be doing is working on those 2 additional control volumes of writing the mass balances for those so we can solve for the additional unknowns that are left, for the remaining unknowns that are left.